So steam enters a well-insulated turbine. So we can sketch a turbine maybe like this. And it has inflow on one end and outflow on the other. Inlet we'll call state 1, outlet state 2. And so that steam, that's just water, H2O, entering that well insulated. So if it's well insulated, often sketch it like this or something like that. And then we have Q dot equal to 0 for what? For a control volume that encloses that steam turbine. So that's our control volume. And so the Q dot entering into that control volume is 0. There's no heat transfer, well insulated. It operates at steady state like most of the devices do. The steam comes in at a pressure P1 of 6 megapascal and a specific enthalpy. They don't give us temperature at 1. And this enthalpy at 1 they do give us is 2952.6 kilojoules per kilogram. Okay. And a velocity, V1, of 12 meters per second. Whenever you see a velocity given, you're thinking, ooh, I better not neglect the specific kinetic energy. What is the specific kinetic energy? It's 1/2 V squared. And so 1/2 velocity 1 squared. Then I'm going to remind you that we often combine it with the enthalpy, so I want to get it in particular units. And it's 1,000 meters squared per second squared is a kilojoule per kilogram unit conversion. And then we can get that specific kinetic energy in kilojoules per kilogram. Let's do that right away. We calculate that kinetic energy of the steam coming in is a whopping 0.05 kilojoules per kilogram. It's pretty much negligible, but let's include it. Okay. The steam expands to the exit where the pressure is, so we would put over here, okay, P2 is given to be 0.08 megapascal, which is 80 kilopascal, which is 0.8 bar. It has a specific enthalpy, H2, of 2438.4 kilojoules per kilogram given, and exit velocity V2 of 95 meters per second. So it's a lot faster. Here we'll go ahead and calculate that specific kinetic energy at 2, and that comes in at 4.512 kilojoules per kilogram. So it's not as negligible as KE1. Okay, continuing to read. The power developed by the turbine, so there's typically a shaft coming out of the turbine, and the power is given to be 6300 kilowatts. Okay, we could add a subscript on there for T for turbine, or subscript CV coming across the boundary, or just leave it without a subscript, either way. Neglecting potential energy effects, so neglect elevation and gravitational change there. Determine the steam mass flow rate in kilograms per second. Well, in this chapter we're studying control volumes, and we're doing the conservation of energy for that control volume. So let's go ahead and write down the conservation of energy. So the rate of change of energy in that control volume with respect to time. Professor, at steady state, that's equal to 0. Okay, well, let's write it down and then strike it equal to 0. And then we're going to have the rate at which heat transfer is coming in across the boundary of the control volume. It's well insulated. It's 0. Then we're going to have the shaft work going out across the boundary of the control volume. Oh, that's given in our problem statement to be 6,300 kilowatts. And then we have the mass flow rate coming in, but also there's only one mass flow rate. The mass balance, mdot1 equal to mdot2. We just dropped the subscripts. It's just the mass flow rate. It comes in at enthalpy 1 and in with the kinetic energy 1, and it leaves at enthalpy 2 and leaves with its kinetic energy at 2. There you go. So it's like we have this value, this value, this value, this value in our problem statement with a little bit of work getting those kinetic energies. And then this in our problem statement, only unknown is mdot. So we solve for mdot, and it's the W dot divided by H1 minus H2 plus KE1 minus KE2. All right, now some people may forget the kinetic energies, and they would just write W dot divided by H1 minus H2. That's not precisely correct, but when you do the math on both of these cases, the first case is going to give us the 12.36 kilograms per second, and that's our answer. But if you made this error and you forgot or neglected the kinetic energy, you would calculate that mdot's equal to 12.25 kilograms per second. You would say, isn't that close? It is very close. It's less than 1% error. It's like 0.9% difference between these two if they just forgot the kinetic energy. So often the kinetic energy effects in a steam turbine are neglected, but for this problem, because you're given the velocities, you want to go ahead and take into account that, their values and have a better answer, more accurate answer. And here it is for part, I guess there's only one part A, if you want to call it that. Well, with that, we're done with this problem. Thank you.